Hey, Michael!
What is it, Michael?
Amber's got a question in the book of yours.
Alright, let's go see what her question is.
Hey, Michael, who invented the fundamental theorem of calculus anyway?
Well, Amber, I'm on my knees, and it all started when Sir Edward Newton sent a letter to Gottfried Wilhelm Leibniz, considering the most basic problems of calculus. My legs are now crossed and I'm against the fence. And problem 1 was that, given the length of space continuously, find the speed of motion at any time proposed. I'm now sitting against a bush, and number 2 is, given the speed of motion continuously, find the length of the space described at any time proposed. I'm now laying next to a lilac bush, and after their deaths, Newton using fluents and Leibniz using quadratures, Augustin Louis Cauchy in the early 1800s was able to create formula proofs. So let me explain that I'm on a swing set, and the part 1 of the fundamental theorem of calculus is: if f of x is continuous on interval ab, then f of x equals the integral from a to x of f of t dt as a derivative at every point x in interval ab, and df over dx equals d over dx times the integral from a to x of f of t dt equals f of x. I now sound like a news reporter. And part 2 of the fundamental theorem of calculus is the integral evaluation theorem, which states that if f of x is continuous at every point x of interval a to b, and f of x is any antiderivative of f of x on interval ab, then the integral from a to b of f of x dx equals f of b minus f of a. Now, before we move on any further, we need to make sure that we have the basics down, or otherwise known as the recap. So, f of x is known as the position function. The derivative of f of x is known as the velocity function. The second derivative of f of x is also known as the acceleration. So then, to reverse it, you use the integral. If you use the integral of the acceleration function, then you have the velocity. If you have the integral of the velocity function, you get position. This is one of the basic properties of the integral. Let's say that you're given the velocity and you want to find y at a given point. And let's say the given point is 77. So then you use the integral of the velocity times dx equals the position function. And with x equals 77, you have x at the point 77, which just so happens to be Jacob's grade. Okay, another property of integrals is finding areas of equations. So let's say that you're given interval from 0 to 3 and the velocity function which equals x. And so you take the time, you graph the equation, and you see the area in which you are solving for. And you set it up as the integral from 0 to 3 of x dx, and you solve it all the way through to x squared over 2. Now you want to take the absolute value of this function, otherwise you're not obtaining to the entire space from 0 to 3. So then you set up everything, just go through the motions, and you get 4.5. And sometimes the integral is just stating that the interval can be set up like a geometric equation. Like, as you can see, this forms a triangle, which you just simply find the length times the height, and you divide it by 2. And the integral is solved that way. It's homework time! It's homework time! Alright, given the interval from 2 to 1 of v of x equals 14x, set up and solve the equation. Pause the video to admire the flowers, and let's go! So, if you actually took the time to pause the video like you should have, this is what you got. You got the integral from 2 to 1, 14x dx equals 7x squared. The interval from 2 to 1 equals 7 times 2 squared minus 7 times 1 squared equals 27 minus 7, which is 21. There you go. Next problem. The following graph follows this rule justly. F equals the integral from 0 to t of f of x dx. Alright, so we have another homework assignment. You're lucky that I'm going nice on you. This is another part of chapter 5.4, but it's kind of the hidden one. So, study this graph, know this graph, look at this graph, like this graph. Let's move on to question A. At t equals 3, what is f of x of this graph? Letter B. If acceleration is at t3, is it positive or negative? Letter C. What is the particle's position at t equals 3 of this graph? Letter D. When does the particle pass through its origin on this graph? Letter E. When is the acceleration equal to 0? No, the answer's not 77. Moving on to letter F. When is the particle moving away or towards the origin of this graph? And finally, letter G. At t equals 9, which side of the origin does this particle lie? And pause the video. Looks like it's time to start some answers. Well then, let's start with A, which happens to be, what is the velocity at t equals 3? Well, what does 3? There's 3. Found 3. What does 3 equal? Oh wait, 3 equals 0. We got letter B here. Just so happens to be, is the acceleration at t equals 0 positive or negative? Well, let's see. At t equals 3 equals 0. The derivative of 0 is 0. And the second derivative of 0 is 0. So I'd have to say that the answer is neither, because it's 0. We got letter C here, and that is, what is the particle's position at t equals 3? Well, you want to start with an antiderivative of 0 to 3 of f of x. That happens to be the area of a triangle. So you take 1/2 of 3 times 6, and you get negative 9, because that just so happens to be a negative 6, not a positive one. Let's work our way up to letter D, which asks, when does the particle pass through the origin? Well, if you have t at 6, and you take the integral from 0 to 6 of f of x dx, you get the two triangles, which just so happen to be the exact same. So 4.5 minus 4.5 equals 0. So when does the origin pass through the particle? Oh wait, that's reversed. When does the particle pass through the origin? It's at s of t equals 0 when t equals 6. E is an easy one. When is the acceleration equal to 0? Well, let's just look at the graph. When does the slope go from positive to negative? Let's look at the acceleration graph. Oh wait, 0's at 7. The answer is t equals 7. We be rocking that letter F. Just so happens to be, when is the particle moving towards the origin or away from the origin? Well then, 0 to 3, you can tell it's moving away from the origin because the slope of the graph is negative. From 3 to 6, you can tell that it's moving towards the graph because it cancels the negative slope away. And from t is greater than 6, you can tell that it's positive, demonstrating here, moving away from the origin.
moving away, moving towards, moving away, and win. Let's finish this off with a letter G, which asks which side of the origin does the particle lie at t equals 9. Well, we already determined that from 0 to 6 just so happens that it be's at the origin. So from 6 to 9, that area definitely looks positive. So if you just make a simple, silly little graph here, which has no actual numerical meaning, it still lands on the positive side. So what's the answer? Oh wait, it's positive. So listen up, babies, you got another homework assignment. You gotta find dy dx of y equals the integral from 0 to x of t cubed minus t quantity to the 5th power dt. Go! This is what you should have solved with. Y equals the integral from 0 to x of t cubed minus t quantity to the 5th dt. Then, you'll find the derivative of dy over dx equals d over du times the integral from 0 to u of u cubed minus u quantity 5th times dt times du over dx. Using u substitution here, you didn't quite catch my drift? Well, u equals x and du equals 1 times dx. Then bring it down to x cubed minus x quantity to the 5th power times 1, otherwise known as du over dx, equals x cubed minus x quantity 5th. Congratulations. You're welcome.
Chapter 5.4 End.